Let's then talk about SUN tensors. So we have shown that QI is a fundamental, it's a fundamental rep. QI upstairs is an anti-fundamental rep. How do we build bigger representations, right? So this is n-dimensional, and this is also n-dimensional. One is called n, the other one is called n bar. So a general SUN tensor will have the following form. It'll say have I small n lower index, J small m upper index. I'm using lower n and upper m because I don't want to confuse them with this n. So under SUN, we have for the lower index, these are fundamental indices, so we will have n factors of SUN vector, SUN matrices. So we get U1, L1, I2, UI2, L2, dot, 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 U of I small n, L small n. And then we get M factors of U dagger, which is J1, say, J1, and let's use M. M we already used, so let's use K. K1, so U dagger, J2, K2, dot, 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 U dagger, JM, KM, and then we have T, and T will have L1 dot dot LN downstairs index and K1 dot 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 KM upstairs index. Okay, so this is a I might call it an MN tensor. Okay, and this is a tensor. It lives in a space which is in an n factor of Q I downstairs and n factors of m factors of Qi upstairs. So this is a space it lives in. This is in general, it's a highly reducible space, but that doesn't. But this tensor may be irreducible depending on how that'll be encapsulated in its symmetries and stuff like that. We'll see soon. Okay, so that's the general MN-SUN tensor. And so how do we build these tensors out of our basic objects, which are Qi and Qi upstairs? We build them by combining different kinds of this. Suppose we have Qi and then say Pj, which is another tensor, or Qi prime, Q prime I, or we have Q prime I upstairs. We can combine these things in various ways to find those higher dimensional tensors. But how do we combine them? We use invariant tensors. So there are these special tensors which are invariant under SUN transformation. And the first one is delta ij. So under SUN transformation, this is a fundamental index. So we'll get UIL, delta L. And here we'll have K will be U dagger of JK, right? But we see that we can then use the delta, the Kronecker delta to do one of the sums. So I get UI, L becomes K, U dagger, J of K. Of course, this is just a U dagger, which is the identity matrix. So I get delta ij. So we see that this is indeed a invariant tensor. However, delta ij with both integers and downstairs is not invariant, right? Is not invariant. Because in that case, we'll just get two factors of u, which will not cancel each other. We won't get a factor of u dagger, right? Is this clear? Is this clear why this is not invariant and this is?
Because both of the indices are downstairs.
Yeah, exactly. Okay, so now suppose our group was SU3. So for SU3, so this is an invariant tensor, epsilon ijk. So if you had SU4, it'll be epsilon ijkl. Okay, so this is an invariant tensor. How so? Let's see. So under a transformation, we will get ui, I prime, uk, k prime, uj, j prime. Sorry, I should have read. So epsilon I prime, j prime, k prime. But we know from the determinant, definition of the determinant, this is nothing but the determinant of u times epsilon ijk. But for the SU and SU3 matrices, the determinant of u is 1, right? So we get 1 times epsilon ijk. So we see that this is, for SU3, this is an invariant representation, right? So there's another one, which is epsilon ijk, but upstairs, because there we get determinant of u dagger of epsilon ijk upstairs, but u dagger is in the SU, it's in the same group, so this is also 1, right? So those are the invariant tensors that one uses to make bigger, contract different fundamental and anti-fundamental representations to make bigger ones. Okay. So, for example, if I ask you the question, is Tij an invariant? Suppose Tij is some representation, okay? Now my question is Tij an irreducible representation? What do you think?
Is this the symmetric thing that we were looking at, or is this just in general?
No, there is no symmetry because one index is downstairs, one index is upstairs. So there is no symmetry involved. If they were both downstairs, we could talk about symmetries, but there are different kinds of indices. Okay, let me ask the question in a different way. Can you extract from Tij, some linear combination which is invariant under SUM? Because if you could, that part would have to be subtracted, and therefore this whole thing cannot be irreducible. Is there like a subset of this tensor that is irreducible? Let me give you a hint. We saw that Qi was irreducible, was a scalar. And therefore, it's one-dimensional, so of course it's irreducible. Can we do something similar here? Can we use one of these tensors here? Can we use, say, delta or epsilon to do something to it that will make it, that will, you know, extract a scalar out of this guy?
Could you like use two deltas to contract the indices?
Why two?
Like one for each of them, I guess. I'm not sure if that's how it works, but that was my idea.
Okay, let's see. You said let's use two deltas, I, J. So we have JK and JL, but this is just gives me, sorry, okay, this to be grammatically correct, I should be this should be delta JK and delta IL. But this just gives me delta
Li, I think, right?
delta JK delta IL. So this should be KL, right? So we get back the same thing. So we are not really done anything.
Oh yeah, that makes sense.
I mean, you can use one, right? You can use. And this has exactly the same index structure as this guy. So it will be a scalar. So the trace of this guy, Tij, the trace of this, the trace is a scalar. Okay? So if this was not traceless, then it cannot be irreducible. Does it make sense? So you can write this as, let's take Tij and divide it into, say, tau. What is tau? Tau is Tii, which is the trace part, which we can write work from Tij using the invariant tensor delta. And then there is another part which is, say, tau ij, which is Tij minus this trace part, which is tau, and let's divide it by n, and then put delta ij here. So now if I look at the delta ij of tau ij, we see that the first guy gives me tau, right? The second guy gives me, I have delta ij and then delta ji, tau over n, but this is essentially the trace of a identity matrix. So I get tau minus n, tau by n. So that means that we can cancel these two things, and therefore this is 0. So we see that this object, as we have constructed, is trace-free, and this is the trace part. And because the trace part transforms in a way that is, it's a scalar, this must also, this cannot be, so, that this, this object decomposes into a trace part and a trace-free part. Okay, so this is the kind of technique that we use to find, just because we have, so for example, if I give you, say, Qi and Qi upstairs, you can say, well, Qi, Qj, let me just call this some, f of ij. Now, so this is a new representation, right? the idea is that this is a new representation, but although this is irreducible, this guy isn't. So if we take, what will happen is that this guy is n, they're taking n tensor n, and then what will happen is we will get a scalar part and a part which is n squared minus 1, plus 1. Okay, so this is how this will decompose, and this is exactly the construction I've given. Okay, so okay, is this clear? So everything here, I've not proved it, but everything here will transform amongst itself, and everything here will transform amongst itself. The dimension of this thing is suggestive. Why is it suggestive? Does this number have any significance for SUN? Can somebody tell me?
Is the dimension of the manifold, I guess.
Is the dimension of the group.
Yeah, I mean the group.
Yeah. So this actually turns out to be, this representation turns out to be, so there's a representation of the group which has the same dimension as the group. What is that? What is the name of the representation? There is a adjoint representation, right? So this is the adjoint representation. It turns out to be the adjoint representation, okay? Okay, so, I mean, I'm not expecting you to become experts on these tensor methods today. I just wanted to give you a flavor, and so that at some point in the future, when you do have to study these things, you have a point of departure, or you can refer back to some notes or something like that, okay? I just don't have the time. Okay, now let's give some more examples. So suppose you have a representation Qi for SU3, of SU3, you can consider epsilon ijk qj, this will be a new representation, an antisymmetric representation, okay? But the dimension, you can show that the dimension of Qi is the same as the dimension of Tij because of the antisymmetry, right? Is this clear why it's, so what is the dimension of Qi? Can someone tell me? For SU3. This is the fundamental representation. What is the dimension of the fundamental representation? Can somebody try? Okay, what are the dimension of the SU3 matrices? The defined 3 by 3, right? So what kind of vectors will SU3 matrix act on? The fundamental 3. So what is the dimension of Qi?
3.
Right, 3. So the claim is this is also three-dimensional. And it has 3 independent components, right? Because of the antisymmetry here. Because I and j takes the value 1, 2, and 3. Because of the antisymmetry, there is not 9 independent elements. It has 3 independent elements, right? Right, because of the antisymmetry of the epsilon tensor. Okay, is that clear?
Yeah.
Okay, so now if I have 2 representation Qi and Q prime of I, So if I combine them, qi, q
Plus.
prime of I, sorry?
Sorry. I was
Yeah.
unmuted.
So if I have qi and q prime of I, this is a scalar representation. You know, we have. So let me make some comments about, you know, what other representations are possible, and then move on to discussing SU3. Okay, so actually, I don't really need to. I just want to say something about the adjoint. So adjoint representation is essentially a fundamental times the anti-fundamental minus a, like the identity. So this has a lot of applications in physics, especially in particle physics, and yeah, high energy physics.